Okay, hi everyone. We're going to go ahead and continue about our integrations, working about what is integration. So, what is it? Well, let's look at the practical application of what a derivative is. So if I ask you guys, if I give you the problem 3x plus 2, and I ask you to take the derivative y prime, this gave us just 3, right? And what is 3? 3 is the change. And in Algebra 1, we call this a slope. Right? Pretty much, it tells us how something is changing at a specific point. If this was a function, y is x squared plus 2, x plus 1. Okay, so this one isn't obvious what the change is. For a simple line, we learned in Algebra 1, it's just a 3. We could have just taken the 3, not a problem. And when we took the derivative, it just reaffirmed that was a slope. Okay, but for a problem like x squared, it's not obvious. So we're going to say, hey, this is really going to be 2x plus 2. Now, y prime. Now, the slope is changing in a parabola here. So this parabola looks something like this right here. And the change, oh, whoops, wrong way. Over here on the left side. Yep, on the left side. And then the slope changes, it's negative slope here, 0, and then we have positive slopes here, right? So negatives and then positives. And that's kind of what we see here. If we say 2x plus 2 is equal to 0, we see that 0 as x equals to negative 1. That's reflected here. The slope is 0 at negative 1. Show you a little number line here. Negative 1. We had 0. On the right side of it, if I plug in a 0, 1, 2, or 3, the slope would be positive. Take a look. The slope is increasing. And if I plug in a number on the left side, like negative 2, negative 3, negative 4, we know the slope, it would be negative, right? The value here would lead us to be a negative value. So as you can see here, this is decreasing, which is kind of cool. So we can actually apply derivatives to say, hey, this isn't just a thing that we do, but this actually tells me something that's happening in the graph. Now, what is an integral in this now? Derivatives give us the change. What is integral? And now integration here, let's talk about integrals. What integrals do is they give us the area underneath the curve. This is a simple way of looking at it. Area underneath a curve. That is a simple, super basic definition of it. Okay? The more accurate definition of it is what we call cumulative change. And that's the big one. Cumulative change, it sounds really fancy, but cumulative means additive. Okay, it's additive. And change is, of course, the difference between one spot and another. So we're adding all our changes together. That's what integral really does for us. It gives us a cumulative change. Now let me give you a dumb example of this. If I give you the equation y is equal to 3, okay? Y is equal to 3. Now I'm going to go ahead and graph this. This might be a little silly, but let's go ahead and graph this. The graph would look like a graph that looks like this. 1, 2, 3. And the graph, let's do this in a different color here. Everyone would be okay with this is the graph of y is 3. Okay? Now, we're going to introduce something also here today of a definite integral. So we're going to say y is 3, the integral of 3 dx, and we're going to say between 0 and 4. Okay? So this is what we call a definite integral. And it's definite because we have a starting value and an ending value. Okay, we have a start and end. And this refers to starting from 0 here, and we're going to go all the way to 4. Okay. And what this is saying here is tell me the change from 0 to 4 of the graph of a simple basic graph of 3. What is the cumulative change? What is the added values of all the parts from 0 to 4? Can anyone give me a guess? What is the added value from 0 to 4?
12?
12. Yeah, that's exactly it. It's 12. And in this case, it's a simple rectangle. You would say it's just 4 times 3 equals to 12.
So we just add the x value basically.
Not add it. We are pretty much figuring out our base times our height essentially. Okay? And now here is the actual representation. 3 is my function, right? That's also my y value. And dx is a little bit of x. Dx means a little small difference of x. And this little s shape here, our integrand, that's the idea of sum. So we're going to add up all the little bits from 0 to 4 of 3 times a little bit of dx. Now let me go ahead and draw this again right here. If I add this little line plus this little line plus this little line, if I keep adding up all these little lines, eventually they would fill up the whole rectangle, wouldn't they? And that would give me the value of 12. Okay, so let's actually take the integral here and let's see if it gives it to me. Now I'm going to show you guys how to take a integral with of a definite integral. So we take it like we normally would. We would say it's 3x. Okay, the integral of 3 is 3x. I'm going to draw a bar from 0 to 4. Okay. After we do this, we're going to say this is equal to, we're going to plug in the 4 and the 0. How do we plug in the 4 and 0? We say 3 times the top, which is x, minus 3 times the bottom. Plug in the bottom. Now, this is going to be done a little funny. We're going to say the integral of, let's do, I'm going to try to think about a way to make sure you guys can understand this. Real quick, let's do the derivative of f of x is f of x, okay? Let's say this. The derivative of big F is little f. So the integral of little f is big F. Okay, are you guys okay with me going forward and backwards? The derivative of big F is little f, but the integral of little f is big F. Okay, so going backwards. So I'm going to write this on the right. So if the integral of a to b of little f is equal to big F of b minus big F of a. So this is a rule for us. And that's exactly what we did. We took the integral of f, giving me capital F, and then we subtract the b from the a. And we'll see this done a couple more times, okay?
Mr. Cole,
Yes.
what does it say next to the integral logo? Is that an S and an A?
Oh, so that's a b. B, I'm sorry, letter b. A to b.
Alright, thank you.
Yeah, of course. I'm sorry, my bad. Okay. So our first step is we took the integral, and then next step is to plug in our x value as 4 and 0. Now, this gives us our answer 12, exactly what we were hoping to get.
What does the line represent?
The line is just a way for us to separate, us to make sure we write our 4 and our 0.
Okay, thank you.
So this carries over here to the right. That's what it does. So we're going to do another problem very similar to this, and you guys can kind of see this. Okay, so that's our super basic with a constant, right? We take the integral of a 3, it's just 3x. And then how do we plug in our definite integral? We just go plug in the 4 in the x value and plug in the 0 in the x value. And that's our result. And 12. And that looks like 12, doesn't it? This looks like 12. And that's what we call our area underneath the curve, our cumulative change. Okay. All right, I'm going to give you guys another example real quick. And it's going to be the integral. Let's say 0 to 2. And the function is going to be a simple graph of, let's do 1/2 x. Okay. I'm going to graph it to the right just to show you what 1/2 x looks like. Here's my graph on the right. We're going to go from 0 to 2. I'm graph from 0. If I plug in 0, 1/2 0 is 0. Plug in 2. 2 divided by 2 is going to be 1. This is the graph. But I only care about from 0 to 2. Now, looking here, what does the area underneath this curve look like? It's going to be, we can use our simple equation. The area is equal to 1/2 base times height. 1/2 of 2 times, this is a 1, right? Is 1. Answer is 1. Cool. Let's actually take the integral of this problem. Let's see if we can remember all the steps we're supposed to do. First, we take the integral. This is 1/2 x 2 over 2. Okay. And if it's a definite integral, here's a new rule. If it's a definite integral, we don't have to write a plus c. No plus c. No plus c. Why? Because we're not guessing the constant that we're going to add. We're going to go ahead and plug in our definite 0 to 2. Take a look. I always copy our a to b right at the end. We draw a little bar, a line, and we write 0 to 2. Then we're going to plug in the 2 and the 0. It's going to be upper minus lower. So I'm going to rewrite this as 1 over 4, okay? Make our lives a little easier. So 1 over 4, plug in 2 squared, minus plug in 0 squared. This becomes 4 over 4 minus 0 is 1. Same answer.
Mr. Ko, will questions ask for us to do it like with the equation and for us to do it with the graph?
Today we are going to work on approximations. I'm just kind of showing you like the end story. That if I take the integral of something, it actually gives me the area underneath the curve. And with these simple, nice simple shapes like a rectangle and a triangle, it seems obviously true. Okay, obviously true. But then we're going to get into shapes that are not rectangle and triangles. We're going to do parabolas, and parabolas are curved surfaces. Just like us, when it comes to finding the slope of something, if it was a nice line, that was easy to find the slope. But once it became a curved surface that was constantly changing, then it was harder. And that's where calculus really kicks in. It deals with these harder problems. Okay. Now, here's the big thing that we want to make sure we understand about this integral. It really is doing what we're doing here, but in a nice, super cool way. Because this is still my f of x. This is still my y value, right? And isn't dx a little bit of x? Which is almost, you could say this is our height and our base. A little bit of x and a little bit of y, when you multiply them, it gives you a little rectangle. And that's actually what we're going to do today. And today we're going to do, these two are, why do integrals work, is we're going to do approximating where to go. So we're going to do approximating the area underneath the curve using rectangles. Okay, so we'll talk about why this basic idea works. I mean, why does integration work? Okay, so here's our first idea. Let's say if I give you a curved surface. Say from 0 to 4. Okay? And it's some type of function, 0 to 4. I want you to find the integral from 0 to 4 of f of x. But this is a graph f of x. So we can do this a couple different ways. First is we can just draw one big box from 0 to 4 and say, that's good enough, right? Would this be a good approximation or a kind of a crappy approximation? Kind of a bad approximation, right? So we say, you know what? Let's give ourselves more boxes. Go ahead and break this up into 2 boxes. Now, how do we frame these 2 boxes? Go ahead and make this into 3 boxes. Eventually, we'll hit a point where we have so many boxes that you're pretty much following the curve. Now, does this idea seem a little similar to what we've been doing before? We start off with a big option and we shrink to something super small. This idea happens when we were talking about slope. If you remember when we talked about slope before. If I talk about slope and I pick 2 points that are very far away, would that be a good approximation for slope at the point here? The blue dot. Nope. And we said, hey, what if I pick a point that's a little closer? Pick a point a little closer. Pick a little point that's closer. Pick a point that's closer. To where, how far are we close? We're pretty much going the limit as x approaches 0, right? This idea we're going to take with us when we're doing integration, but we're going to go ahead and jump on board using something pretty simple. Today we're going to do approximations, and we're going to talk about 3 different approximations that we're going to do. We're going to do something called left-hand rectangular approximation, left rectangular area approximation. Oh, sorry, area method, abbreviated Lram. We're going to deal with the right version, right rectangular area method, abbreviated Rram, and Mram, which is the middle. So the idea is, before calculus, we had this idea of how do I find the area underneath the curve? We could draw rectangles like we did up here, but as you can see, if it's a curved surface, it is not easy to get a good answer. So the trick was they would break it up into smaller rectangles. The more rectangles we do, the more accurate our drawing. This is almost like pixels. If you guys know anything about pixels and computers and graphics, we started off with Mario Brothers, which was an 8-bit, and if you remember Mario Brothers, it was very super blocky. And then, well, that wasn't Draw Mario Legend. And then we eventually went to Mario 64, and then now we're at Mario Odyssey, whatever. And you can see that the graphics change. And the reason why it looks better is because instead of using big bricks to model graphics, we end up using very fine pixels that ends up approximating the curve quite well. And that's kind of like our method of math. We're going to start off with real big blocks, and we're going to refine that so that our size, our limit here of our dx is as x approaches 0. So what's the width of our base? It's going to be so small. The width of our base here is going to be so small, it's going to be practically 0. So let's first start with something easy. I'm going to go ahead and jump over to the worksheet I have for you guys today. And the statement is, for each problem, approximate the area underneath the curve using 3 left endpoint rectangles. So I want you guys to look at this because this is already drawn out for you, and on IXL, sorry, in CUDA, you guys will be looking at this. Let's look at some characteristics. Here is first the function. You guys all notice this is the function, this is the graph, right here. Making sure our y-intercept is 3, and our slope is rise 1, run 2. Everyone cool with this? This is just the graph given. And here is our a to b. This is our a to b. I want you to say this is a definite integral from -4. Take a look here. This is -4 to 2. -4 to 2. And the question says, please break this up into 3 left endpoint rectangles. So I want to break this up from -4 to 2 into 3 separate sections here. Now, given this breaking up into 3 different sections here, we have a choice. We can actually draw these rectangles a lot of different ways. We can use what we call a left endpoint. If you take a look here, I want you to notice that at each of these points, we have the left side touching the graph. You guys all see this, the left side touching the graph? If we want to draw rectangles, that left point will be our y value. So what is the area of each of these rectangles? And then we're going to add them up. This is going to be 1, 2, 3, okay? So my height is, this is a 1 by 2. Take a look here. Isn't the base 2? 2 spaces? Triangle. This here is going to be a 2 by 2. And this here is going to be a 3 by 2. We can add those up. The area is going to be 2 plus 4 plus 6. Our approximation for this area is really 12. And that's it. But my question is the real area 12? Is the actual area of this 12? And you can see that I actually left off a lot of air here, didn't I? But this is why we call this term Lram. Because it's a left rectangular area method. It is just an approximation. It's our basic, elementary school way of figuring how much is covered using basic shapes. Okay, let's look at using the same exact question here. We're going to look at the right-hand method of it. So go ahead and copy this problem again if you can. Or you can just take a look here. It's actually going to be pretty easy. So we have our left-hand approximation. Let's take a look at what our right-hand approximation would look like. If I instead chose the right side, so we have our dots. Take a look at the blue dots. Now I want you to follow along. In my first rectangle here, I'm going to take a look at my first rectangle, okay, my first interval. Which would be my right value? Would it be the 1 or the 2? Which of these would be my right value, the 1 or the 2? Hopefully you would say it's going to be the 2. Thank you, 2. So what I would do here is I would draw the rectangle out from the 2, and this would be my rectangle. Does that look like an over approximation or under approximation?
Over.
It looks like over, right? Do you see I'm over the line? And that's fine. Look at the next interval. Let's take a look at the next interval here. Would I choose the 2 or the 3? I'm seeing from the right, I would choose the 3. And that would be my next rectangular approximation. My last interval, would I choose 3 or 4? I'm going to choose 4 because we said right. So for my right Rram, my right rectangular area method here, my approximation, we would use 2 times 2, 3 times 2, and 4 times 2. That's going, the area would be 4 plus 6 plus 8, and this is going to be 18. Now we can see that this is an over approximation, and this is an under approximation. And you might say, Mr. Cole, why don't we just use a triangle to measure it? And we totally could. But careful, this isn't a triangle, right? It's more like a trapezoid. We could use a trapezoid to approximate it. Okay, so we learned 2 methods right now. We use our Lram using our left endpoint, and then we use Rram using our right endpoint. Now, none of them were the best method. So if you can't use them, you can't use the right, you can't use the left, you can't use the right, why not try the middle? And that's another one. We mentioned it as my Mram. Okay, so this one's going to be a little harder, but the values aren't terribly hard here. But let's go ahead and take a look here. Okay. So what is the middle value between -4 and -2? That's at -3. So take a look here. What is f of -3? And if I plug it into the function, right, or I look at the graph, that looks like it's going to be, let's just draw it. Let's draw it out first. That looks like it's going to be 1.5. So this is 1.5. Looking at the next interval, what's the mid value here? Well, at -1, this mid value here, that would be my next midpoint approximation. Over here between 0 and 2, that would be at 1. And this one is almost, take a look at it, it's almost like it's the best of both worlds. It's a little bit over, it's a little bit under. You guys can see it's a little bit over, it's a little bit under. Right, it's a little bit under here, but yet it's still a little bit over. A little bit under, a little bit over, a little bit under, a little over. So the midpoint is another type of possibility. So this would be, this looks like it's going to be 2.5, and this is 3.5. So we're going to say this is 1.5 times 2, 2.5 times 2, and 3.5 times 2. So that would be 3 plus 5 plus 7. Right, that was a 3.5. And this approximation is about 15. So we had 3 different answers here. We had, if we all agreed to use left point approximation, our answer would have been 12. If we all agreed to use Rram, our approximation would be about 18. And if we all decided to use Mram, midpoint approximation, our approximation would be 15. Okay. So this is what you're going to do in today's homework. You're going to approximate the area underneath the curve using the rectangles that are given. Now, what is the actual area underneath the curve? Well, the actual area underneath the curve, let's go ahead and write the integral here. The integral of x over 2 plus 3 dx between -4 and 2. If you take a look, I wrote everything we had here in an integral. Let's examine this one more time to look at the parts. We have our interval from -4 to 2. That's our -4 to 2 here. That's when we want to start up and end. We have our function. This is our f of x. That's our y value. And we're going to multiply this by a little bit of dx. So let's go ahead and solve this integral here. This is going to be, you can see this as a 1/2 x. So the integral would be 1 over 2 x 2 over 2, power rule, plus 3x. Okay, the integral of 3 is just add the x between -4 and 2. So please take a look. If I actually did the integral, a process that we practiced before, using power rule, and then we're going to plug in our a to b. So this is going to look a little funny, but take a look here. I'm going to rewrite this as 1 over 4x squared, okay? Make our life a little easier. We're going to plug in the top minus the bottom. Plug in the top minus the bottom. So let's plug in the top, which is 1 over 4, 2 squared, plus 3 times 2, minus the bottom version, which is 1 over 4, -4 squared, plus 3 times -4. I want to pause here to make sure you guys catch everything I plugged in. Step 1 was simply just take the integral. Just take the integral. Step 2, go ahead and plug in your interval, f of b minus f of a. Plug in the 2 minus plug in the 1. If you notice, I wrote an extra parentheses here, just in case you guys can see. I wrote an extra parentheses to make sure everyone's being subtracted. That backside is all negative. It's going to be all flipped. Okay, we can simplify the math. 2 squared is 4. 4 divided by 2 is 1. 3 times 2 is 6, minus 2 squared over here. No, 4 squared is 16. 16 divided by 4 is going to be 4, minus 12. Negative is a positive 12.
You mean -12?
Oh, negative, and then I took this negative here.
Oh, yeah, okay.
Okay.
There you go.
Thanks for bringing that up, yeah. So everyone, you can see I did get a -12 here, and then I multiplied it by that negative in the front. So when we by the powers combined, this is 19, 15. The actual area underneath the curve is 15. So Mram was actually pretty good at guessing it. In this case, because it was a line, it was actually really a lot more close. And of course, we knew that Lram was going to be under, and we knew Rm was going to be over. Okay. So today's homework, really, you're just going to practice just doing what they ask you to do. If I'm looking for a left-hand approximation, let's take a look at this next problem here. Oh, sorry. To make sure you guys can still see that. The graph is drawn already for you. So all these problems, the graph will be drawn for you. The interval -4 and 1 to 4. I want you guys to make sure you know that this is from 1 to 4. They asked us for 3 rectangles. Sure, 3 rectangles. 1, 2, 3. To see we broke into 3 parts. And since I'm choosing the left endpoint, let me switch colors. My left endpoint here, left endpoint, left endpoint. So looking at this section here, my left endpoint was either going to be 4 or 3. So we choose 4. Between 3 and 2, we choose 3. Why? Because we asked ourselves, we said left endpoint. Between 2 and 1, or 1 here, we choose 2 because we want our left endpoint. And you're just going to add up the rectangles.
Are you always going to choose your left endpoint?
It's all depending on the question. That's a great question from you. If you looked at the original question, it says choose our left endpoint rectangle. So that's how we're choosing left here.
Okay.
As I move to my next question here, it's going to actually ask me to choose my the right endpoint. So that's our Rram. And if you notice, let's take a look here. You get a choice. Here's my first interval, second interval, third interval, okay? First interval, did I choose the left or the right? We chose the right one. Left or the right, we chose the right one. Left or right, we chose the right one. And why do we choose left or right and not choose the best? The point isn't about choosing the best right now. The point is making sure your answer and my answer are the same because we both did the same process. If we both say left, we better start left. If we both choose right, we better start right. There is another method called inscribed and circumscribed. Inscribed and circumscribed, which means you're going to choose values inside or outside Okay, and we'll talk about that later on. But we're dealing with our three basic methods right now: left, right, and midpoint. If you look at this graph, this is right, right, right. See the interval? You get a choice. You choose left or right. We chose right here. This problem here, though it's super curvy. Do you choose left or do you choose right? We are choosing right. Choosing right. So you end up drawing a rectangle on that right side. Even if it's over or even if it's under, it doesn't matter if it's over or under, we're going to choose the right. Looking at this one here, from -4 to -2. -4 would be up here and -2 would be over here. Which point do we choose? If we choose left, we would be up here. But we're not choosing left. This was a right problem, so we choose the right endpoint. Given our next choice, right here, do we choose left or do we choose right? We chose right because this is the right problem. Choose left or choose right? We said choose right. And you draw a rectangle based on that. The idea is to make your curved surface into an easy rectangle problem. All right, this next one is going to be midpoint, okay? Sorry, this one is still right. This is right. Right.
But Mr. Ko, I have a question.
Yes.
So when you choose right, middle, or left, one of those will always end up the same answer as if you plugged it in. No.
The other one, it just also happened because it was a nice, easy triangle, and the spacing worked out perfectly.
Oh, but you don't always plug in like -4 and 2 into the like equation thingy.
We can do that if we want to find the exact value.
Okay.
When we actually find the integral, it actually tells us the exact value, not some dumb approximation. But to get to that idea of what an integral really is, we have to learn how they did this before that. And that was done through approximations using rectangles.
Oh, so right now we're only doing approximation.
Right.
And then like tomorrow or whatever, we're going to go on to
find the actual one using integration, yes.
Okay, thank you.
So it's almost like we're primitive cavemen, like just breaking stuff with stone, and then we eventually get to like, 3D printing ourselves. Okay. So if you look here, this is some crazy triangle thing. Well, we can approximate it using, and this method is midpoint. Okay, this is midpoint. So I want you to take a look between our first interval here. Take a look at this interval here. The midpoint is not left, it's not right, it's in the middle of the graph, meaning it's where -5 happens. What is f at -5? Okay. The next one is, it's not -4, not -2. What's in the midpoint here? It's at -3. What's the -3 value? Now sometimes it might be unclear what that value would be if you're looking at the graph. You would then have to plug it into the function. I'll plug a -5 into it, I'll plug a -3 into it. And that's what's going to happen when the problem is not nice. Like this parabola here, take a look here. The midpoint is not nice. Between -1 and, so -3 and -2, the midpoint is going to be right here, -3.5. And that's not really clear what that value is. So you're going to have to plug in -3 into your y function to figure out what that value would be. Now for this rectangle, if you take a look here, what's the base of the rectangle? That's going to be 1 times whatever this value is going to be. And you're going to have to use a calculator. If you want to be cheesy about it, go ahead and use Desmos. Copy this function into Desmos, and then just click at 3.5, and you'll -3.5, and you'll see what the y value is. Or just spend 2 seconds on the calculator and plug it in. Okay, and that's really what your homework is today. Homework is to practice finding left, right, and midpoint approximations using rectangles. So that's Lram, Rram, and Mram. Now, I gave you guys actually like 5 questions here where I didn't graph it out. Take a look at these 5. I didn't graph it out. You're going to, in this case, they're easy, right? But if not, just go ahead and go on to Desmos, write this equation on Desmos, and then break it up into, this case, 4 sections. So think about where your intervals would be for 4 sections. And then pick your left, right, and mid, and go ahead and give me a rectangular approximation to that. Okay. Now, I would recommend you draw a easy light version. So if you're drawing this on Desmos, you're going to draw it out. And this graph is going to be at 1, 2, 3, negative 1 over 1. So the graph looks something like crazy graph like that. Now, this graph goes from negative 7 to negative 3. That's the interval I want you to figure this one out. Okay, so for this one, I think this is the actual question for 19. So I need to break this into 4 intervals. And lucky from negative 3 to 7, that's actually 4 separate ones. 1, 2, 3, 4, something like this. Now, if you read the question, I want to use, for each problem, find the approximate area underneath the curve of the given using the left endpoint. So I'm going to use the left endpoint. Let me erase this. My left endpoint, my left endpoint, my left endpoint. And you're going to have to find out what those values are. If it's on Desmos, you have the numbers already. If not, you plug it in. What is negative 7? My first value is negative 7. Negative 7, negative is a positive 7, plus 3 is 10. That's going to be 10. So 10 times, the space here is going to be 1. That's my rectangle. 10 times 1. That's my first value. Second value is at negative 6. If I plug in negative 6 there, it's going to be 9 times 1. Then follow 8 times 1. And then 7 times 1. Okay, and we are going to add all those up. 10, 9, 8, 7, 6, 15, 25, I think 34. And it's just going to be 34. That's me adding up all 4 rectangles. Okay. That's it.